Hi, welcome back. This is a shop talk for December 2025 and probably second to last video for this year. Maybe the last video, depends on how things work out. And I have a few small things to show you, and maybe something interesting is within this pile of footage. So let's have a look. So I needed a super simple power feed that can go extremely slow for the compound slide of the lathe. And before I go into detail, disclaimer, I know that CNC machine exists, I know that servo drives exist, and I know that stepper drives exist. No need to tell me that in the comments, thank you very much. So I needed a way to drive the compound super slow and relatively smooth. Slow as in about 1 revolution per minute. So in other words, awfully slow. And for me, the easiest solution is a DC motor with a gearbox. So I found on eBay a motor with a 1... this is quite funny. There's a 1 in 3000 gearbox. I had it open. It's a worm gear reduction and then a stack of regular spur gears. It's awful build quality, to be honest, and if this proves to work very well, I will get something, a nice motor, something like a Faulhaber motor or a Maxion or something like that, something decent. This is just proof of concept. So 3D printed a little bracket. I didn't want to drill into the machine, so I just bolted in. I used existing hardware. I will show you how it mounts later. So I 3D printed this, turned a pulley out of Delrin that mounts to the motor, and I welded a belt out of polyurethane round stock. I can show you how the welding works. That's really not very hard. And this belt rides in this groove of the graduated dial of the compound. This, conveniently enough, works quite well. And I made the belt to a length, so I don't need any belt tensioner. It just stretches over here and is good to go. I don't have a controller or something like that. I'm just using my power supply. And I'm plugging and unplugging banana jacks, because that's the easiest and simple solution that I had on hand and didn't have to buy anything. So you can see on the hand crank that it's moving. It's moving this direction currently. To change orientation, I have to do this on the banana plugs. In the other direction, the motor is even louder. I suspect the design is not meant to be reversible. If this proves, well, it already has proven out to work exceptionally well for what I need. I will get a nicer, some high quality motor with a nice gearbox that doesn't sound like it's dying every second. I already tore it down and filled it with a high body grease, but this direction really sounds awful, and I think it's grinding itself to death. Fortunately, I don't need that feed direction for the work I'm doing. I need this direction. So, got lucky there. Yeah, as I said, this is really just a proof of concept. I had to do 40 parts, and for consistency's sake, I got sick of hand feeding hand over hand with 1 revolution per minute. So that was my solution for this. So let's swing it around and look how this mounts to a lathe. Different day, different setup. I just wanted to show you that I can, even with the belt in place, I can still position the slide. So I don't need any clutching apparatus for this ultra fine feed. And I've used this a few times now, and it works marvelous. It has no right to work that well. but it does. So to take it off the machine and get the machine back in the normal tool room conditions, take the belt off, and I have 2 screws. This is number 1, and it's a very long screw, very long thread engagement, rather unnecessarily, but well, it is what it is. Yeah, that's it. We're back in full normal mode. And the way this mounts is, didn't want to drill any additional holes, so what I did is I took these M6 socket head cap screws that hold the bearing shield in place, and I drilled and tapped an M3 thread into them. Means these 2 screws act as the mounting points for the drive motor now, without having to modify the actual castings or parts of the machine. The screws can easily be replaced if I'm ever bothered by the 2 M3 threads in here that nobody will ever see or notice. So I guess that's a very low impact modification to the machine. And while I'm here, there's also this. When I work with the 3-jaw soft jaw chuck and flood oil and 1000 RPM, despite having this guard here, this flip down guard, there is still a lot of oil coming to the front here and creating an utter mess. So I 3D printed this shroud that goes over this diameter behind the spindle and semi-clamps to it so it can be spun in place. And this catches 99% of the oil that goes out the front. It can be very easily taken off. I kind of have grown on solutions that are easy to be taken off, not permanent modifications. So this comes off like a few seconds. There we go. Ugh. That's just 3D printed PLA, and this piece here has 2 melt-in threaded inserts. And as you can see, it's oily, but it works great. It really works very well. Here you can see me roughing away most of the material with a regular DC GT insert for aluminium. Just taking like a 2mm deep pass, hand feeding. Hand feeding because the Powerfeed is way too slow. This would take forever. Changing to the monocrystalline diamond tool, and I take 2 passes, one to rough away, well, to semi-finish the surface, just by hand feeding, to remove any topography left from the carbide insert. And then I take a 10 micron depth of cut finishing pass with the Powerfeed. And this leaves the desired surface finish that I'm after for these parts. And here's the finished part. There we go. Another diamond cone finished. Well, not diamond cone, diamond finished cone. I want to show you how to weld these polyurethane round belt. This is 4mm round stock. This is a standard industrial item. You find these in all sorts of applications, mainly as a drive belt for small horsepower motors, as a transport belt in many cases, where you use them in pairs, like a conveyor belt. And there are other applications too. For example, you can insert short pieces in things like robot grippers or end effectors to increase grip when you need to pick up something slippery. You cut a little bit of a dovetail, you press in a bit of this polyurethane round belt, and that gives you something grippy and a little bit conforming to the surface you're working on. So these best hot weld. You mirror weld them, and there are special devices and fixtures for that, or you do it with things that you have laying around. What I use is box cutter blade for welding with a heat source. I have this tiny butane torch here, something to cut the blade, and that's it. In my case, I have two V-blocks for alignment, which makes it a little bit easier, but you can absolutely freehand it, and you need a bench grinder with a grinding wheel. I just cut the ends off the belt stock freshly clean off, so there is no oil or other contaminants on it, and I just clamped this box cutter blade in the vise. I would like this to be below the surface because I want to weld up here so I can loop the belt around. So you heat this up to a little bit under red heat. So if it glows a little bit, it's fine. Gives you a little bit more time to act. There's a little bit of red, dark red glow. That's fine. And you just press the belt against both sides of the blade, so you melt both ends. Just like this. Until you get a nice molten surface. Then you butt it up against each other, and you hold it until it's cooled down. You could build a cool fixture to do that, where you switch, where you can lower, where you have two stationary V-blocks with a little bit of a clamping arrangement, one of them sliding back and forth to allow the weld movement, and a swing down blade that you heat up. You swing down, you melt both ends, you swing the blade out of the way, and you slide the two V-blocks together. That's how industrial mirror welding fixtures work. This process exists for tiny diameters like this round belt, but the same way you weld like a 300mm diameter PVC pipe in a chemical facility. We had a millwright at day job who built a large mirror welding fixture for in-house use because the commercial options he didn't like those, so he built one with large flip down heater. So once this is cooled down, you have this weld seam here, and you need to clean that up. In the past, I tried to slice it off with a razor blade, and that does not work. Well, it does work, but it doesn't look nice. So what works way better is bench grinder. I don't have a bench grinder in the shop. I use the wheel of the Deburr grinder, and you just clean the weld seam up until you hit parent material, and then you end up with a very, very strong and good running belt. There we go. You can see the weld seam here, but it's cleaned up and ready to go. It's that easy to make a round belt. Round belt stock, every industrial supplier will have it, and I'm 100% sure that you will find it on eBay. If you're in the US, McMaster has it 100%. I cobbled something together to ratchet tap these holes by hand, just using the milling machine as a guide. I ground a little bit of a flat on the tap on the D-bit grinder. I took a M6, a long nut, extension nut, drilled it out to the shank diameter of the tap, so it fits over here, and I drilled it for an M4 set screw. M4 set screw with a flat tip. This locks on here. And I have this small ratchet from Vera, which has a through hole. Now I can very, very conveniently support the tap from the back either with a bushing or with a spring-loaded tapping guide, and use the ratchet to tap away. Little idea that I wanted to try for quite some time now. Tapping the holes M8x1 using the ratcheting tap holder that I just showed. I have a spring-loaded tap follower in the spindle, and I already did one, and I have to say this works quite nice. So spring-loaded tap follower is in place, supporting the rear end of the tap. Cutting oil. And I have to say, this works super nice. I think I will make me a bunch of these hex adapters for different size tap shanks. And this allows to tap very, very sensitive. The horizontal spindle of this mill does not have a quill, so power tapping is a little bit annoying without a floating tap holder. There's probably a million different ways to do it, but that's the way I have chosen to do it. You have to be a little bit careful, I guess, because you put side load on the tap. That's why I kind of want to support it here a little bit. And you could force it out of the tap follower if you're not careful. But doesn't seem to be a huge problem. Instead of the spring-loaded tap follower, I could also use a drill chuck, a keyless chuck, and leave it open a tiny bit so it guides the rear end of the tap, but allows it to rotate. Well, it doesn't have to be a keyless chuck for this purpose, can be a keyed one too, but the keyless ones are all I have. In the teardown of the indexing head, I briefly mentioned that I'm looking to get a digital readout for the indexing head. Means some form of rotary encoder. The space constraints around the indexer do not allow something like a shaft encoder, because I need a through bore and I don't want to elongate the spindle with an extension for various reasons. So the next best thing is to either a hollow shaft encoder, which are usually fairly small on the through bore still, or an encoder ring. Heidenhain makes optical encoder rings that you can buy and integrate in your design. They are rather expensive, means with a single axis readout they are somewhere in the mid 4 figures. But they are deadly accurate. That's nice. So I bought the next best thing, and that's this encoder ring from AliExpress. And, well, would have been nice. But sometimes stories are too good to be true. This combination is supposed to have 1 micron resolution across the circumference. This is a 122mm OD that gives a fairly fine readout. And for a test setup, I just took a piece of Ratchet polyurethane foam. I milled a precision diameter onto it where I can press this ring on so it's constrained. I tried it beforehand, just sitting on the spindle of the indexer and bumping it through, and that went nowhere. It gave me terrible results that were super unreliable. But with the ring now constrained, running through and round, and also planar run out being very good, because I machined the shoulder where it presses up against. Now I get repeatable results. So I hooked up the read head of the encoder ring to the Z-axis of my DRO. If this was a viable option, I needed either a 4-axis readout or a separate single-axis readout for the indexing head. I would be okay with both solutions. But let's see. I can enter like an angle here. I don't think you can enter like angle, arc seconds, arc minutes. You can only enter decimal degrees, but you can set the readout to show degree, arc minute, arc second, which I kind of prefer, I think. Not entirely sure, but most engineering drawings I work with have their angle callouts in degree, arc minutes, arc seconds. So there's that. And yeah, when I crank the indexer, the readout follows along. Quite nice. I can zero it out in every position that I want. That's nice too. And overall, just seeing this and kind of playing with it is super cool. I really enjoy it, and I think this would make for a great option on indexing head. That's all fine. That's working well. But the problem is the accuracy of this thing. I'm not entirely sure what's going on. So I crank the dial to 0, double checking. Yeah, that's pretty good on 0. And I zero out that's basically the C-axis. C, not Z. So the rotational axis along the Z-axis. A would be along X, B would be along Y-axis, and C is along the Z-axis. So zeroed that out, and now I crank to an arbitrary position, like let's just go by 10 degrees. Oops, overshot a little bit. There are the 10 degrees, using a magnifier to line up the lines nicely. So you cannot say that I didn't give it my best shot. And the readout is reading 9 degrees, 59 arc minutes and 27 arc seconds. So we're 33 arc seconds off. That's not horrible. That's within the original spec of the indexing head. Keep in mind, I have checked the worm gear in this indexing head for multiple positions for precision, and it came out pretty good, better than 30 arc seconds. So I'm prone to trust the dial and the worm gear combination more than this unknown encoder ring. Let's crank to something else, Let's go to 90. Or do something off. 90, 91, and so this will be 91 degrees and 30 arc seconds. I have to use the magnifier because I'm very far away from the dial because of the camera. So there we are. That's 91 degrees. That's good. 27 arc minutes. That's not good. And 7 arc seconds. That's 2 arc minutes and 35 arc seconds. That's almost 3 arc minutes error. That's a bit much, to be honest. I already knew this before I started to record. I played around with this for the entire afternoon already. And the problem is this error is absolutely not linear. So you cannot easily map it out. That's the first problem. The second problem is it's not repeating. So these problems that I'm seeing with repeatability and linearity on this Magnet Encoder Ring match the problems that I've seen in the past with cheap linear magnet encoder systems. No repeatability, no linear accuracy, and the error was not linear either. So kind of useless for my limited knowledge. There's probably people who know way more about it, but this doesn't impress me at all. Could you make it work? Maybe. Maybe you could map out the error and somehow deal with the repeating error. You could use it as a rough readout and for precision use the dial, but that's kind of sketchy and hokey. Not a big fan. So I guess the answer is a good optical encoder with a very high number of counts per revolution, not this magnetic encoder ring. So I'll try to get this off this. If you want to know where I got this from, I purchased this on AliExpress. I will link it down in the description, but you have seen what I got. It is exactly what I ordered, but this entire setup was $150, included shipping. That's probably a reason why the digital readout on my surface grinder costs with 2 linear scales like $5,000. Here is a close-up of the magnet ring. As you can see, this is an injection molded part. Here are the ejector marks where they push it out of the mold. And I suspect this is a conductive plastic or a plastic with a high ferrite or iron content and can be magnetized. And if you take one of those magnet viewer screens, we can see the indexes, the spacing of the encoder ring. So that's quite neat. Would be nice if all of this worked together so well that it gives a nice result. Here's the read head. It has an LED that shows when you have a good signal against the ring. What I learned is that the runout radially and axially is super important with rotary encoders. Thanks for that. Somebody helped me understanding that. The distance of the read head to the ring can also be important, but the manual gives you the maximum distance. So this is the encoder that I tried to use. It's supposed to have a maximum read distance of 2 millimeters to the ring, but they recommend 1 to 1.5 millimeters. And it's a TTL system, so 5 volts square signal. Would have been super nice if this worked out. I planned to put this on the back of the indexing head where it's completely out of the way. That's the back side of the indexing head. And my idea was to have it on the back side here, out of harm's way, not influencing either the adjustment of the direct indexing discs, nor block the ability to use a drawbar in here. And the reed head would mount on the casting over here, and I would have a little bit of an aluminum housing to protect it all from damage, just from hitting it with stuff. So that would have been super nice, but not with this encoder solution. I'm going, the search continues. The amount of experimentation I can do with different rings is of course limited. This is going to get expensive very quickly. So I guess next try will be an optical encoder. Unfortunately, you need a quite high resolution to make it practical. I mean, the dial of the indexing head reads, the smallest divisions are 1 arc minute, and you can interpolate half arc minute on the dial. I was worried that I might lose my credibility as a machinist cosplayer here on YouTube, so I went out and got a 125mm diameter 4-jaw independent made by Zentra. All the chucks that I have for the Weiler lathe are made by Zentra, and while they are not high quality, they are also not bottom of the barrel. They are very, very solid, good, a good starting point for a chuck. They usually need a little bit of fettling out of the box, like a little bit of deburr, but overall fit and finish is quite decent. My 6-jaw chuck that I use daily and my 3-jaw dedicated to soft jaws is really very nice, both with fine adjust to get run out. But yeah, now I added this 4-jaw independent, comes with a spring on the chuck wrench, which we don't need of course. And yeah, fit and finish is quite nice. I had the jaws already out. I'm not going to take everything apart. As far as I can tell, it's relatively clean. The grease in here is clean. There is no black grinding dust in it, so that's a good sign. All that I'm going to do is well, probably have to take it apart because I want to deburr, for example, these edges here, which are razor sharp, and also these leading and trailing edges on the jaws, which, when they are sharp, they will scrape away material over time from the guides. And also I want to use a different grease. The grease feels okay, but I want to replace it with this stuff, Molykote P1042, which is a white grease and it's ultra sticky. This is an actual chuck grease. An alternative to this stuff would be, in my opinion, something like Molykote G Rapid, which is a molybdenum disulfide grease. But I'm going to use this for the first time. Want to try it out. I would have preferred a chuck with an integral mount for the lathe with a short tape of 4, but I also wanted a 125mm chuck. The smallest 4-jaw independent that I could find with a short tape of 4 internal was 200mm diameter. But since I'm doing a lot of small parts, I figured I want a chuck that's not enormous big because of the RPM limitations. This chuck, it's a cast iron body, but it's allowed to run 2500 RPM. And I just noticed that the laser engraving is super aggressive, and the face of this chuck definitely needs some stoning. And I purchased a backplate blank. So this has already the taper and the face machined. Comes with the 3 studs that fit the lathe, and the front side is just flat. So you just have to machine the register step and drill 4 holes to screw this thing together. Hitting the front face of the chuck on the sanding plate. To knock down the raised burr from the engraving. Going to hit the back side of this on the sanding plate too. The sanding plate This is a very inexpensive surface plate from the woodworking store with some silicon carbide paper glued to it. Robin has done a video on these and its uses. It's basically a super large precision ground flat stone, and it's a mixture of inspection tool for raised areas burrs and also a tool to remove said burrs and raised areas. So super useful, not very expensive to get a hold of. Surface plate was like 50 bucks. And the silicon carbide paper is not expensive, plus a can of spray adhesive. Here I'm cutting down the blank to accept the 4-jaw chuck, and I take 1.5mm wide facing cuts to rough out the centering boss. There is the backplate, all turning work finished. I had to reduce the OD too, because these come at 126 and a little bit millimeter diameter, oversized compared to a chuck. And that kind of looks ugly, so turned it down to the same diameter as the chuck. The register is a close fit, and yeah, it's ready to go. Only need to drill the holes and that's it. The chuck fits nicely, but without any noticeable side-to-side play, so that's good. I think I mentioned it before, but I really like this system of mounting a chuck. It's almost as fast as a cam-lock spindle, but way simpler to make. You loosen 3 nuts, you twist this ring on the back of the spindle, and you give the backplate a light tap so it comes off the taper. Since it's a dual contact, these flanges make contact with the taper first, and then there is a little bit of a gap between the faces, and when you tighten the studs on the backside, you pull the backplate onto the taper. It squeezes itself on there, it's all elastic, until the faces meet. And then it's fully mounted in a very rigid situation. The taper and face contact arrangement, the short taper, is exactly the same as on a cam-lock spindle, but on these you have the through holes for these studs and the bayonet disc behind it. So I kind of prefer this style. It's a little bit simpler, it's less stuff going on. I think the Brits call what I'm doing here fettling. That's basically deburring and hand finishing. I heard this term first when dealing with castings, where you remove the rises and the seam lines and just do general cleanup work. So I'm taking these jaws, using the magnetic ball vise here, which is super convenient for this type of work, and I'm knocking down all the edges that are still sharp. So I'm just using a die grinder with a small cylindrical carbide burr to knock down these edges. I also want to deburr the threads down here. These have a sharp edge and also a little bit of raised burr from however these were made, so I'm going to clean them up too. Same out here. This is just razor sharp, and when this sticks out on the back side of the chuck body and you accidentally touch this while it's spinning, well, you will spring a leak. When I do this, I always take a climb cut, and I take fairly light cuts, but multiple passes, And that leads to way nicer results than when you get greedy and try to cut a large chamfer in one go. Doing the partial threads, just running the same burr along the edges, flipping it around and doing the same in the other orientation. I cannot tell how important I think it is to get good with an eye grinder and hand deburring for a tool room environment. Less a skill for the proper CNC machines, but for me in a tool room environment, this is absolutely valuable. I did a little bit more work off camera, and a good indicator to know when you're done is when you can do this and really squeeze down and move your hands over all the edges and corners and without bleeding afterwards. So that's a good indicator. The last step will be to use a abrasive bristle brush on the drill press and just giving it a once over to remove all hairline burrs and remaining micro burrs and things like that. Hey Stefan, why do you need such a massive drill press? Well, surely not for drilling holes. Most of the time I use it with a tapping head for tapping, or with these, for example, to deburr and finish parts. These are nylon brushes that go in a chuck or in a collet, and these nylon brushes have silicon carbide abrasive molded into them. These are coarse and these are fine. I don't know the grit off the top of my head. Relatively inexpensive. They're like 10 bucks a piece. And yeah, they're a very mild way to remove micro burrs and just finish parts very evenly. By the way, these are also great at throwing parts across the shop. I decided to take out the feed screws for the jaws, and they have these retainer pieces from the back. Marked them with die grinder, their position and number, so rotational position and with a small line, and a number 1 to 4. And they conveniently have a thread in them, so you can use either some sort of a puller arrangement or a slide hammer. Boink. I deburred the body of the chuck off camera, washed it in the ultrasonic cleaner, and I'm about to put it back together. I'm using the Molykote P1024, and yeah, as advertised, it's incredibly sticky. So this is slot number 3, so I need worm number 3, and I need the correct retainer piece that goes in here. And I'm just going to use a little bit of the grease. This stuff is not crazy, not crazy cheap. and it's hard to get in small quantities. I would recommend if you have machinist or home machinist friends and you want this stuff, buy a can of it together and share it, because sharing is caring. This is how I got this little can too. So this goes in here. And I clean my fingers because this stuff is really incredible sticky. And it's also supposed to wash off very badly with coolant, or very hard with coolant, which is not a problem because I don't run coolant anyways. So I align it, and then I use 2 copper drifts to put it back in place. Check if it still spins. Yep, that's good. And the next one, this is slot number 2. But Stefan, with the grease being so sticky, won't there chips getting trapped in the grease? Yeah, sure. That's why you clean chucks from time to time. As I mentioned, molybdenum disulfide grease would also be great for this application. But I want to try this stuff. There we go. That's a once over on a brand new chuck. Let's finish the backplate. Oh yeah, okay. This is basically the test if you did a good job. No blood, so that's good. I would have been hesitant to do this with the chuck out of the box. It would have worked perfectly fine, but a little bit of a deburr doesn't hurt. Over at the milling machine, I set the part up on the indexing head with the 3-jaw chuck clamping from the inside. And I have to drill from this side because I also have to kind of bore it. The chuck has a 4-hole bolt pattern and this has a 3-hole pattern. And matching these in a good way is always a little bit annoying because it's very easy to get intersection problems where you cut into another hole or something like that. So I already figured it out. I need to align this at this horizontal and then spin 45 degrees and index 4 times. Then I get a well-centered hole pattern. For aligning this horizontal, I'm just going to put 2 set screws in these holes. Nice big parallel. And I just push up against it and I take an indicator, indicating it in. I start here at a random number. I just crank slowly. I see that number is rising. That means that I need to spin the part counterclockwise to get it closer to be true. And okay, yeah, barely a movement after after the first adjustment. Even I get lucky at times. Indexing by 45 degrees. This should give me my first hole location. Time to change to a spotting drill. This is only a 8.5 millimeter hole that I'm going to drill here. But I still prefer to pre-drill with high-speed steel drills that are not any fancy modern geometry. It's just, it's easier on everything. Less cutting pressure, less danger of shifting parts in your setup, less force on the machine itself. It's It's all better. Counterboring the mounting holes with a shop-made piloted counterbore. This tool uses a small carbide insert that I ground on the D-bit grinder out of 3mm carbide end mill shank, and the tool itself is just made out of drill rod, unhardened, but it works brilliantly. As you can see, the chip it forms is really nice, and yeah, I'm too cheap to buy a commercial M8 counterbore tool. For a tool that didn't cost anything apart from a little bit of time and knowledge and a D-bit grinder and a lathe and a mill, it works quite well. I'm running it at 400 RPM. The tool wants to chatter a little bit in the beginning, but once the interrupted cut ends and it's taking a full 360-degree cut, it just runs smooth as silk. Deburring the inner edge of the hole in the counterbore. If you don't do that, I will find you, I will come to your house and I will mix up the cutlery in your kitchen. Finished all the machining on the backplate. It came out to my liking, but ooh, what's that? That's the second one. I wasn't sure in the beginning if I should show you this, but this is not the first of those backplates that I machined for the 4-tar chuck. This was the first one. Why did I make a second one? Well, this one worked perfectly fine. The hole spacing fits, the centering register is fine, but there was one thing that was nagging me really, really hard. That was, if you look at those two counterbores and their distance to the threaded hole. It's such a stupid little detail, but this I didn't really take great care when I did the first setup, and I just eyeballed the position, and once I bored the counterbores, I noticed that it looks absolutely stupid that way. Despite it never ever being seen by somebody. But as you can see, this stud even overhangs the counterbore on this side. And that was enough to make me decide to scrap it. Really expensive mistake, to be honest, but I wanted it to be nice. And so I took a second. I ordered 2 blanks because I wanted to have one in storage anyways. Well, I don't have one in storage now, I will keep the scrap one for whatever. Maybe I will plug up the counterbores and grind over it. We'll see. But as you can see here, now the counterbore and the chamfer of the counterbore perfectly clear these studs, and it's evenly spaced to the studs, and all is good. So, well, was this necessary? No. Was it necessary for me? Absolutely. This was so annoying to me. This was so annoying that this happened. Not only that, it wasn't only annoying that the spacing here to the threaded holes was not symmetrical, but it was also annoying that I didn't take care when I did it the first time. So that's it. When you do something, take care of it properly. This goes on here. And another thing that I changed to my first plate, on this one I used a step drill to cut those counterbores. That's a fairly loose fit. Perfectly serviceable. This is a DIN fit, a fine fit by the standards. But on my own designs, I honestly prefer a tighter fit on the counterbores to the screw head. It just looks tidier. So that's the reason why I made the pilot, the counterbore tool here. So, oh, and the screws that came with the chuck didn't adhere to the standard for these screws. Well, they maxed out the tolerances in the plus direction. So I took the screws and I machined the heads a little bit smaller, so they are a nice fit in the counterbore and also run true to the threads. So there's that. Okay, 25 Newton meters. Oops. I don't tighten these down like mad tight or glue them in, because there are cases when I want to remove these. For example, when I use this chuck with the backplate on the milling machine. So that's it. And there we go. There is the 4-jaw independent chuck, all cleaned up, lubricated, deburred, and with the backplate fitted. So ready to be used twice a year. Just because I have them out already. That's basically the 3 chucks, well, 2 chucks that I use on the lathe, plus this one that I just added to the collection. Probably 90% of what I do happens with the 6-jaw chuck. It's just a super good way of holding round stock, since the jaws have less distance between each other. It's a very stable situation if you have only very short stock to grip or soft stock to grip. Also, since it's fine adjustable, really, really nice for precision work. Then I have a 3-jaw chuck. This is also fine adjustable. I couldn't get one with a steel body without the fine adjustment, so that's what I got. Turned out to be quite handy at times. And I use this almost only with soft jaws. And yes, my soft jaws, I make them myself. I just buy aluminum round stock, saw it into discs, and I have the CNC mill the mating contour in the back. Very fast way to make soft jaws. And now I added the 4-jaw independent. One thing that is nice, the chuck is about 15 millimeters shorter than my other 2 chucks with the fine adjustment. The fine adjustment adds quite a bit of length on the chuck body to make it all fit in there. That's a drawback that I'm very happy to live with, because the fine adjustment itself is such a useful feature. It's incredibly useful. So yeah, that's well. What do you want to say? This is a 4-jaw chuck on a lathe. I guess we can spin it. Well, it spins. Let's see. I need to go. Loosen this a little bit, tighten this a little bit, and work my way around it. It has been quite some time that I did this the last time. There we go. There is a reason why I prefer the 6-jaw. It's just more convenient at the end of the day. This might be more versatile, I'll give it that. But if I have to do like 20 parts in a row, this would eat my motivation quite quickly. So yeah, there it is. That's close to zero, run out with a 10 micron indicator. Here's a quick close-up of the counter boring tool. 10mm shank, 8.3mm pilot diameter in front here, and 7mm diameter clearance here. The cutter is a piece of 3mm round carbide and has 5-degree clearance on the underside, 10-degree positive rake, and 15-degree radial clearance angle, so it clears the sidewalls of the bore, and also 5 degrees of secondary radial clearance to the top, so it doesn't rub on the full length of the edge on the wall of the hole. Goes inside. It's just a piece of hot roll that I use to test the tool. And the tool goes inside the pilot bore. A little bit of burr on there. And you can use this tool even in a drill press. It doesn't need to be a milling machine. What you see down here, making contact with the workpiece, this is the main cutting edge, creating the floor surface of the counter bore. When we spin it by 90 degrees, you can see the clearance down here behind the cutting edge. And also the 10-degree positive cutting angle here. When we stick it in the counter bore, the cutting edge is in front here, and behind it it's all clearance. So that's all the necessary angles on such a cutting tool. It's relatively simple. The only trick on this tool is, if you look at it, the hole for the tool is not on center line. It gets even more apparent when you look at the face. The set screw that's holding the cutting tool in place is offset by 1 millimeter, and so is the 3mm hole for the cutting bit. And I did that so when I ground the tool, the cutting edge itself ends up on center line, and I keep as much as possible carbide. If I put the cutting tool on center line, I would have to split the carbide in half, and that wouldn't even give me a positive cutting angle yet. That would be a 0-degree cutting angle. If I went for a positive cutting angle with a split blank, I would have to remove even more carbide. So that's the reason why it's offset. And the cutting bit is ground completely on the D-bit grinder. Very simple tool. In the last video about the rebuild on the decal indexing head, I mentioned that I'm going to replace the damaged washers, which are standard thin washer, with heavy-duty fixturing washers. And not everybody seems to be familiar with these. They are a commercial off-the-shelf item for fixturing, and there is a whole assortment of parts available. For example, nuts that are 1.5 times the thread diameter tall. There are a little bit less tall nuts, but with a large flange. There are large washers with a spherical cutout, and the tall nuts have a spherical end on one side. And of course, these mate together and allow for a little bit of angular disalignment. This is, for example, kind of important when you do setups on a milling machine with strap clamps and the strap clamp is not perfectly horizontal, this will allow for a little bit of alignment or being out of alignment in all directions without putting weird strains on the threaded stud or pushing or pulling on the part. That's the big type, and there is also a smaller diameter one. And these are heat treated. They are not really hardened, but they are in the 20 to 30 Rockwell C range compared to these, which are in the no Rockwell C hardness range. These are soft like butter, and these are more like, yeah, 2-day-old pretzel. Look in any tooling catalog and you will find them. McMaster has them for sure. Misumi sells this stuff. Hoffman has a lot of it. You will find it if you look for it. So what I figured, I'm going to order these heavy spherical washers. They are the same diameter as the original one. They are thicker, so they are not as prone to get squished and deformed. And I combine them with these nuts. Unfortunately, the T-slot screws are a little bit short. They are dimensioned for regular 0.8 times thread diameter height. The 0.8 times thread diameter height, what that means is it's a M12 nut, 12 millimeter diameter. 12 times 0.8 is 9.6, and that's the height of the nut. That's a standard nut, and these are 1.5 times the thread tall. So since I don't want the nuts to look all funny with partial engagement, I'm cutting them to the same height as the regular ones. I already did a bunch of them, and this is how they look. They are still a little bit taller. So I still get the same thread engagement. I get the bonus of the spherical end, which allows for a little bit of and I get the bonus of these very, very heavy washers. So that's my idea behind this. Quickly shortening these fixture nuts, since they're only available in 1.5 times thread diameter height, and I need 0.8 times thread diameter height. So just removing 8 millimeters from the end and cutting a new chamfer inside and outside. Using a CNMG insert running 1900 RPM, just taking 2 or 3 cuts to reduce its length. And there we go. There's the reduced height fixture nut. I cut the chamfer usually big enough so I get a full round face here that does not intersect the flats of the hex anymore. Some people call that a washer flat. Man, this feels really like I'm grasping for for content, but that's the indexing head, and I'm replacing the original nuts one by one with the heavy-duty fixture washers and the spherical end nuts. And I'm doing them, of course, one by one, so I don't have to retram them once I'm done. But I guess that's kind of obvious. I wonder how boring this would be if you watched it in real time. There we go. I don't torque wrench these, I just give them a good yoink on the wrench. So yeah, that's the indexing head with the hardware replaced. Super exciting, but I wanted to show you the heavy-duty washers, so I guess might be informational for some people. So yeah, that's the indexing head with the replaced hardware. Not exactly groundbreaking content, but I think not everybody knew about the fixture hardware and also the possibility to repurpose it for other things. So that's all for today. These Shoptalk videos are always nice for me to edit because I can get rid of my shorter video clips and projects that are not suitable for a full-length video. And yeah, they're quite fun to edit, so there's that. And since we're coming to the end of the year, depending on if you celebrate, what you celebrate, have some nice days. Hopefully you have some days off from work or studying or school or whatever. Make the best out of these days, no matter if you're alone with friends or family. I'll be back next year. I'll be working between Christmas and New Year, but that's self-chosen. That's on me. No need to pity me. Thank you all for watching. Thanks for the support. Thanks for everything, and see you next year.